Hello and welcome back. Today we're going to review Unit 12 on probability. This wasn't too large of a unit, so it's not going to be too many topical reviews in this one, so we only have one video. But here's an overview of what to expect. Okay, we'll have some basic terminology, some formulas, before we get into a few slides with some topical reviews. Here's an overview of the lessons that we had in this unit. Okay, so just pause a moment, just refresh yourself on what we learned. Here's the first slide of Common Core Standards. As a reminder, these are the standards that are used to create your Regents exam in a few weeks. So pause the video now, get a sense for them so you can know what to expect. And here's the next slide on the Common Core Standards. So again, pause the video now and get a sense for what the standards are asking you to do. Now with probability, there's a lot of terminology that's involved, so it's important for you to be able to be familiar with these terms. I'm going to go through these one by one and kind of talk about them a little bit. An experiment is simply just some process that occurs with well-defined outcomes. So for instance, pulling marbles out of a bag, or flipping a coin, or getting a heart when you're dealing with a deck of cards. Okay, that's an experiment. The outcome is the result from one single trial. So when you flip a coin, you might get a heads. When you are pulling marbles from a bag, you might pull a blue marble, and so forth. Okay, when you're dealing with cards, the next card might be a club. An event is what you're typically looking for. Okay, it's a collection of one or more outcomes. Say you want to know the probability of getting a heads. Okay, the event is going to be every time that you get a heads, or every time you pull a blue marble, or every time that you flip and get a spade. The sample space is going to be a collection of all possible outcomes of an experiment. Okay, so for flipping a coin, the sample space is heads and tails. For pulling marbles out of a bag that have red, blue, and green marbles, your sample space is considered number of red, number of blue, and number of green. So you could have 20, 15, and 7. Okay, depending on how many of each marble there are. Your sample space could be the number in each suit. So for heart, clubs, diamonds, and spades, it's going to be 13, 13, 13, and 13. Okay. Your theoretical probability versus the empirical probability. Now this is talking about either the theory of the situation, which is talking about the mathematical scenario for all possible cases, or the empirical, which talks about what's kind of given to you, what data is given to you. So you might have like a two-way frequency chart where you have male and female, and you might be comparing it against event A or event B, what their preferences are. Empirical probability is when you're dealing with given information. Say we have 2, 5, 10, and 17. Okay, that's a set of empirical data. Theoretical probability is talking about all possible outcomes. So if you're looking at a population, so that's more applicable for things like pulling marbles out of a bag, where you know the total number of things, or when you have flipping a coin or a deck of cards. That's more dealing with theoretical probability. Empirical probability typically deals with two-way tables, okay, or some kind of data given in some kind of way. Conditional probability is a formula for that, but essentially conditional probability occurs when you're looking at one particular event, and out of that one particular event you want to know the probability that something else is occurring. Okay, so but it's looking at one particular event. So if you have a Venn diagram, which we're going to look at in a moment, you have two events A and B, and you want it to be conditional on event B, you're only caring about anything that appears in circle B. Everything else you're not caring about at all. Okay, you're not even considering them. So that's what conditional probability is. We're going to have a slide on that specific topical review in a moment. And the last term is independent event. Okay. Now independent does not mean separate from each other. Sometimes the word independent, It sounds like it should mean something different, but it doesn't. In terms of probability, two events are said to be independent if the probability of one event occurring has no effect on the probability of another event occurring. Okay. And with independent events, in actuality, there'll actually be always some kind of an intersection. Okay? There'll always be some kind of overlap. But the probability of one does not affect the probability of another. And there's a formula that we'll see for that in a moment to help determine if two events are independent or not. So there were some formulas that we had in this unit. The basic definition of probability for an event occurring is essentially what you want, which is the favorable, over the total possible outcomes. Your value of your probability will always lie between 0 and 1, or between 0% and 100%. Because 100% is equivalent to 1 and 0% is equivalent to 0. Okay. You'll never get a probability of 2 point something. So if a question asks you which one of these is a possible or an impossible probability, should I say, anything that's greater than 1 or less than 0 is not going to be a possible probability. Likewise, anything greater than 100% or less than 0% is not a possible probability. And that might be a good multiple choice question you're going to see. There's another formula, the union formula, which we dealt with dealing with sets. And the union between two events, A and B, is always going to be found by taking the probability of A plus the probability of B and taking away their intersection. Because when you add A and B and there's an intersection, you don't want to account for that intersection twice. You're going to take away that intersection once. Okay, that gives you the union of two events. Notice there's important symbols. If you have probability of A, let me write this a little better. Okay, probability of A union B. So I was going to write better, but I didn't. A union B. That is the same thing as probability of A or B. Probability of A intersection B. When you see that, that's talking about the probability of A and B. Okay. It's important to make those connections between the symbols and the words. Okay. Now the word or is going to be an inclusive or, meaning that it's not one or the other. It's going to be one or the other or both. Okay? Because both occurring means that at least one of them occurred. Okay, the next formula is the conditional probability. Now that is notated like this. Probability of A given B. Okay, so whenever you see the word given, that's typically implying conditional probability. And what that is going to be in terms of a formula is the probability of their intersection of A and B divided by the probability of B, because you're only caring about B. The condition in this case is event B. You're looking out of that total event B. What's the probability that A occurs? Well, it's where A and B intersect. Okay, because you're not looking where they don't intersect, just where they intersect. So in terms of a picture, if I drew event A and event B, I'm only caring about event B, because that's what I'm out of. And where does event A occur given B? Well, it's their intersection of A and B. Okay. Lastly, the test for independence. The probability of one does not affect the probability of another, which means that the probability of A given B will be the probability of A. Means if you're given another event, the probability of getting A is going to be the same. So the probability of A given B is the same as the probability of A. You could also think about it in terms of the other way around. So the probability of B given A, well, that's going to be the probability of B. Okay, that's the test of independence. Notice if I substitute in the conditional formula for the test for independence, that I can actually rewrite it as this. Probability of A and B over the probability of B is equal to probability of A. So some people also use this substitution to rewrite the formula so that it looks like this. Probability of A times probability of B is equal to the probability of their intersection. Okay? That's also an acceptable formula to use to find out if two events are independent, because if you multiply the events together, you get their intersection. Then it's equivalent to the test formula. Okay? But I've seen some places where they accept that use. Okay. Pause the video now, write down anything you need to before moving on. A big part of probability is being able to create a Venn diagram for a situation. Now, for Venn diagrams, it is important to note that all values must be accounted for from the sample space. So if you're dealing with things in terms of percents, they must add up to 100%. If you're dealing with things in terms of numbers, they have to add up to the total number of things. If you're dealing with probabilities, you have to make sure that they all add up to 1. Okay? So you have to make sure that all values from the sample space are accounted for. So, for instance, and a Venn diagram looks like this, right? You can have a Venn diagram with two events. That's the most common kind. There has been some Venn diagrams that deal with three events. I'm just going to kind of draw over the numbers here. So 3 events intersecting. Okay, you're probably not going to get higher than that, A, B, or C. Okay, because having 4 events intersecting each other is very complicated. Okay, we're not going to worry about that. 3 circles is probably the biggest you're going to get. But most of the time we're dealing with just 2 events. Okay, so I have a couple of examples here dealing with Venn diagrams and how to fill them out. So if there is a 50% chance of event A occurring and 45% chance of event B occurring and a 14% chance of neither occurring, draw the diagram to illustrate this sample space. Okay. So I'm given things in terms of percents. So I'm going to probably keep them in terms of percents. But I have to remember that everything in this diagram has to add up to 100%. I have to make sure you account for everything in the sample space. Well, I know there's 50% in A and 45% in B, but I don't know what their overlap is, so I have to find that out in some way. There's a 14% chance of neither occurring, so what I'm going to do is I'm going to put a 14 outside the circles in this bottom right hand part of the diagram. There's 14% of neither occurring, and that's actually going to help me figure out what the intersection is going to be, because if I add 50 plus 45, I get 95%. But what I will have inside has to equal to 100 minus 14, which is 86%. That's going to tell me what my overlap is going to be. So if I subtract these two things, 95 minus 86, I get 9%. So 9% must be my overlap. Another way you can do it too is if you add the 50, the 45, and the neither, you'll get 109%. That also indicates your overlap as well, 9%. Okay. But either way, now we can figure out the rest of this diagram. So event A is 50% chance of occurring, so that must mean there's a 41% remaining that is in circle A, because everything in circle A must add up to 50%. And in circle B, we must have a remaining 36%, because 36 and 9 make 45. Now it's a good idea to just add everything up just to make sure everything adds up to 100%, and 41 plus 9 plus 36 plus 14 adds up to 100%, so we're good. Okay, so there's our Venn diagram illustrating the sample space. Now this is in percents now. Okay, so if you have a total number of outcomes, for instance, if there are 250 outcomes, I can fill this diagram out in terms of the number of events. Make it a little bit larger because now we're dealing with 250 things. Event A and event B. To do that, all I have to do is just I have to multiply 250 by the percent. So 41% of 250, 9% of 250, 36% of 250, and 14% of 250. So if I take 250 and times it by 41%, so notice I have to convert it to the decimal, I'll get 102.5. So the equivalent part in this Venn diagram talking about the number of outcomes is 102.5. Doing the same for the other percents, don't forget 9% is 0.09. I get to 22.5 as their intersection. 250 times 0.36, that gives me 90, so 90 goes there, and 250 times 0.14, that gives me 35, so 35 goes here. So that's in terms of the total numbers of outcomes. Now, in terms of probability, if you're dealing with theoretical probability, we're going to keep it as a decimal, even though sometimes they're talking about number of people or number of things, and you really don't have half of a thing. Okay, but we're going to keep it as a decimal because that represents the theoretical probability. Okay. Now, in terms of interpreting the results, let's say I said, what's the probability that you have A and not B? So the intersection of A and not B, so that's a symbol for not, the little tilde. I'm looking at this part right here. And if I'm talking about in terms of number of things, I'm not going to write 102.5, I'm going to write 103. Divided by the total, which is 250. Okay. Well, okay. If I'm talking about the number, sorry, I should say that a little better. If I'm talking about the number of things in A and not B, I'm not going to say 202.5, I'm going to say 103. Okay. Alright. Pause the video, write down anything you need to before moving on. Let's take a look at conditional probability. So just recall the probability that A given B is going to be the probability of A and B divided by the probability of B, your condition on B. So let's draw a Venn diagram to help illustrate this first problem. Out of 25 people, 10 are male, 14 own a car, and there are 3 males who own a car. Okay, I'm going to draw the Venn diagram over here. Now notice I'm not given things in terms of percents or probabilities, I'm given things in terms of numbers. So I'm going to use a Venn diagram consisting of the number of events. Okay. I have to think of what are the two events? Well, I have males, and I have own a car. Now as you label them, you might want to label them with letters that represent the situation. Don't always label them A and B, unless on the side you make a little key that says A is this, B is this. But sometimes it's helpful just to use the letters of the problem. Okay, if you want to say OC, own a car, that's perfectly fine. Okay, I'll just have M and C. Now notice there's complements to every event, right? If you're a complement to a male, it's going to be a female. Anyone who's not a male is a female. Anyone who owns a car, the complement to that is not own a car. So the complement to owns a car is not own a car. So it's important to know what each part of the Venn diagram represents. This part right here represents those males who do not own a car. This part represents the males who own a car. So male and no car, male and car. This part represents female and car, and this neither represents female and no car. Okay, so it's important to know what all these numbers are going to represent, okay, and what each part of the diagram represents. So let's start filling this out. We know that there are 10 males, but I don't know which is it going to be 6 and 4, is it going to be 7 and 3, I'm not sure yet. There are 40 people who own a car. Again, I can't fill it out yet, but 3 males who own a car. So here's where the males own a car, right there, intersection. Using that information, I can fill out the rest of this diagram. There's 10 males, so there's a total of 7 males who don't have a car. It is a total of 14 people who own a car, so therefore 11 people who are female own a car. And if I add all that up, I get to 21, which means I have 4 left over for a total of 25. So there's my diagram in terms of number of events, number of outcomes. Now it says find the probability that a random person chosen is female given that they own a car. So what we're doing is we're finding the probability that they're female given that they own a car. So we're looking at just the number of people who own a car, which is 14 people. And out of those 14 people, how many of them are female? Well, looking at the diagram, we have 11. Okay? Because the intersection of own a car and female is 11. Now you might think, well, 3, but that's the intersection of male and have a car. So be careful about that. Okay. Out of the 14 who own a car, the question is which ones of them are female? Well, it's going to be not male, so it's just 11. Now you can write your answer as a fraction, 11 over 14, and I think that's actually preferable. And even if you don't reduce it, that's fine as well, because without reducing has a little more meaning to the context of the situation than reducing it does, I think. But you might be asked to say percent or probability as a decimal. So if it says nearest hundredth, then it might be something like 0.79. Or nearest percent, you might ask to write as a percent, 79%. Okay, just type in your calculator and find the decimal. Now let's look at the next one. Find the probability that a random person chosen owns a car given that they are a male. So we're looking at the probability that they own a car given that they are male. So we're looking at just the males in this situation. So it's only 10 males, so we're looking at just the 10 males. In that Venn diagram, how many of them also own a car? 3. Okay. So you can leave your answer as a fraction, 3 out of 10, or as a decimal, which is 0.3, or as a percent, 30%, because all of these in this case are exact answers. Okay, there's no rounding needed. So all of them would be acceptable in my book unless it says specifically how to leave it as a fraction, as a decimal, or as a percent. Okay. So that's conditional probability. Pause the video now and write down anything you need to before moving on. Now let's look at independent events. So just a reminder, here's the test for independence. Probability of A given B has to equal the probability of A. Probability of one affecting the other doesn't exist, so they don't affect each other at all. So writing it with a conditional formula, essentially the probability of A and B over the probability of B is equal to the probability of A. Alright, now let's look at this situation. We have the probability of A is 35%, the probability of B is 62%, and the probability of A or B is going to be 80%. So let's use that information to help set up the Venn diagram. Because in order to solve this, we need to know the intersection, which we don't know. We only know their union, which is A or B. So here's a diagram for event A and event B. Now if I'm given that the total of A or B is 80%, I can use that union formula to find out the probability of their intersection. So the probability of the union of A and B is the probability of A plus the probability of B minus the probability of their intersection. Where their union is 80%, so I'm going to keep things in terms of percent, is going to be equal to 35 plus 62 minus the probability of their intersection. 35 and 62 make up a total of 97. Subtract off 97, I get negative 17. Equals the negative of the probability of their intersection. So if I divide by negative 1, I get their intersection is 17%. Which means the remainder of A must be 18 because that makes 35, and the remainder of B must be 45 because that makes 62. I want to find out, just to complete the diagram, because every time you do a Venn diagram you have to add up, make sure that it adds up to the total sample space. That doesn't add up to 100%, but if you add them and subtract from 100 you get 20% left over. Okay. Now the question is, are events A and B independent? Okay. Does the probability of one have no effect on the probability of another. So I can do one of three things actually. I can test the probability of A is that equal to the probability of A given B is that equal to the probability of A. I can test is the probability of B given A is that equal to the probability of B. Or I can use that test that I indicated in the formulas page, whereas if I multiply the probabilities of A and B, does that equal the probability of A and B? Okay. Three ways you can do this test. The technical way of doing it is to use this formula. Probability of A given B is that equal to the probability of A. Okay. That's technically the test for independence. You should use that. But all else fails, any of the other methods should be fine. Okay. So what is the probability of A given B? So given B, we're looking at just the 62. How much percent of that 62 is in A? 17. So 17 over 62. The question is that equal to the probability of A? The probability of A is 35%, so it's 35 over 100. And if you find the decimal approximations, you get about 0.72, but you can see that's not equal to 0.35, so they are not independent. So you can say that they might be dependent on each other in some way, okay, but they're not independent. Okay. Now, in the next example, okay, I give the probability of A, the probability of B, and I tell you that they are independent. Okay, so you're going to assume that they're independent. Find the probability of A nor B. So let's set up a Venn diagram. Okay, here's A, here's B. They're in terms of percents. Okay, so I'm actually going to use this formula up here to find out their intersection, because that's a nice little formula that's rewritten to find the intersection. You just got to multiply the probability of A and probability of B. Now be careful, this is only allowable to use if you are given that they are independent. If you're not given that they're independent, you can't just multiply them to find the intersection. You have to find some other way of doing it. Okay. So the probability of A and B is going to be the probability of A times the probability of B, which is 0.2 times 0.4, which is 0.08. So the intersection is 8%, which means the remainder of A must be 12%, and the remainder of B must be 32%. Now the question says, find the probability of neither A nor B, so we need to find out this part down here. Okay. This right here is neither A nor B. Sometimes you'll see it as not A or B. Or you might see it as not A and not B. Okay, there's different ways of notating that little space right there. Either way, they have to add up to 100%. So I have to find out what the union is. The union is 12 plus 8 plus 32. Or if you use the formula for union, it would be 20 plus 40 minus 8. A plus B minus the intersection. But another way you can find the union, if you have the numbers, just add all the numbers up. Okay, I think that's a little easier. 12 plus 8 plus 32 gives you a total of 52%. So the probability of neither A nor B must be 100 minus 52, which is 48. So, depending on how the question asks you to leave your answer, it might be 48%, it might be as 0.48, it might be a fraction reduced form, so then in your calc you just do 48 over 100 math frac. Anytime you do something math frac, it gives you the reduced form of your fraction, and that gives you 12 over 25. Okay. Alright, pause the video now and write down anything you need to before moving on. Alright, and lastly we're going to look at multiplying and adding probabilities. Now this is dealing with multi-stage events. Okay. Typically, anything that's happening at the same time gets multiplied. So anything happening at the same time deals with multiplication of probabilities. Anything that is being done separately, that is going to be when you add. Okay. Anything that occurs separately is when you add. So let's look at this first example. You have to be a little careful about these because you have to make sure you account for all the different possibilities. A cookie jar contains 7 Oreos and 4 Chips Ahoy cookies. You take 2 cookies from the jar without looking and eat them. What is the probability to the nearest hundredth? So this is indicating how to round your answer and how to represent your answer. So the nearest hundredth that you ate one of each kind of cookie. Okay. So think about this. You're looking at the probability of one of each kind. So if you picked an Oreo first, then your next one's going to be a Chips Ahoy. That's one event occurring, so it's going to be involving multiplication. But what happens if you pick the Chips Ahoy first? You have to consider that case as well. If you pick the Chips Ahoy first, then the next one you're eating is going to be an Oreo. What is the probability of eating one of each kind? A lot of people forget this second step right here. Don't just find this first one and be done with it. You have to consider all different scenarios. You start off with an Oreo, then you go to Chips Ahoy, or you start off with the Chips Ahoy and have an Oreo next. Okay. Now, when you eat them, of course, you're not going to replace them back into the jar. So this is a situation dealing without replacement. Sometimes you have to think about that from the context of the situation. Sometimes they tell you you replace it or you don't replace it. But in this case, I think it's pretty clear you're not replacing them. So the probability of getting an Oreo, then getting a Chips Ahoy, is going to be one event. So this is going to be one set of multiplication of probabilities. Probability of getting an Oreo is 7 out of 11. Because it's a total of 11 cookies. 7 plus 4 is 11 cookies. But there's a 7 Oreos, so you're going to choose 7 of them. 7 possibilities of getting an Oreo. Now, when you eat the cookie, you have a total of 10 left over. Now, if the problem says one of each, 2 Oreos, then I would have had 6 remaining Oreos then, right? But in this case, it's talking about a separate type of cookie. So there's Chips Ahoy. I haven't eaten one yet. So there's a total of 4 Chips Ahoys. So 4 of the remaining 10 could be a Chips Ahoy cookie. So this is one event, and that's why you're multiplying them. Okay. Now a separate event is choosing a Chips Ahoy first. So the probability of getting a Chips Ahoy is 4 out of 11. But then you have to, with the remaining 10 cookies, choose one of the 7 Oreos. Now I got to find the answer by just finishing off this problem. So 7 elevenths times 4 tenths gives me 28 over 110. 4 elevenths times 7 tenths is 28 over 110. Add them up, I get 56 over 110. But this question says specifically round to the nearest hundredth, so I have to find the decimal approximation, which is going to be, let's see my work here, 0.50909, etc., etc. Okay. So the probability to the nearest hundredth is 0.51. Notice it said probability. If it said the percent to the nearest hundredth, then the percent would have been 50.91%. Okay, but that's not how the question was asking. It says probability to the nearest hundredth. Probability is always between 0 and 1. Now let's look at the next example. There are 16 marbles in a jar. 10 of them are blue, and the remaining marbles are red. What is the probability to the nearest tenth of a percent? Okay, so this is going to be represented as a percent. That if you pick 3 marbles, all 3 marbles are the same color. Assume that you replace the marbles before drawing another marble. So this is dealing with replacement. And this specifically said we're going to replace them. Okay, so once you pick a blue marble, you're putting it back in. Or if you pick a red marble, you're putting it back in. So, it says what are the probability that all three marbles are the same color? So what that is asking us to do is find the probability of choosing 3 blue. And we're going to add to the probability of choosing 3 red. Now for the 3 blue, I have to figure out how many total of marbles we have. We have 16 marbles. And each time we replace the marbles back in, so we have a total of 16 each time. Picking 3 blue the first time, how many blue are there? There's 10 of them. Okay. But if you put it back in, you still have a 10 out of 16 chance of getting a blue. And put it back in, you still get a 10 out of 16 chance of getting a blue. So that represents the probability that you get a blue each time with 3 picks. Now for 3 red, again there's a total of 16 inside the bag, but how many red are there? Well, the remaining are red, so there's 10 blue, there must be 6 red. So we have 6 times 6 times 6 on the top. Okay, multiplying this out, we get 1,000 over 4,096 plus 216 over 4,096, which is 1216 over 4,096. As a decimal is 0.296875. So the nearest tenth of a percent, 29.7% chance that you get the same color marble with 3 grabs, with replacement. Alright, pause the video now and write down anything you need to before moving on. Okay, so here's a summary of what you should be able to do from this unit. So first you should know that and understand that the probability of an event occurring is always going to be between 0 and 1, or 0% and 1%. You should be able to use Venn diagrams and tables. We haven't really had too many table examples in this review video, but I mentioned it a little bit earlier on, to find the probability that an event occurs. Okay, so you might need to use those tables to do conditional probabilities or just probabilities in general. You should be able to find conditional probabilities. You should be able to determine if 2 events are independent or use the fact that they're events to find some probabilities. And you should be able to solve problem situations that involve adding and multiplying probabilities. I want to thank you for watching this video, and I look forward to seeing you in the last set of videos on Unit 13, Statistics. Thank you.